So when we're looking at instantaneous change, so instantaneous is the gradient of a single point. Now, if I asked you that, right, if you're talking about a single point on a coordinate, on a point, you're talking about here, there's a gradient of a single point. Now, the gradient of that could be anything if it's a single point, right? So wouldn't the answer be this infinite? Because, I mean, technically you could have any gradient, and also undefined, because, you know, if it's going straight up, then it would be undefined. So, you know, you could have possible answers of these if it was just a single point. So instantaneous is the gradient of a single point. A single point, I'll probably argue with that, because you could argue this thing here where it's just one point. Well, what's the gradient of that? Is it straight? Is it upright? Is it down? Is it not? So as I'm saying, I'm being a bit more of the devil's advocate here with some people's responses, purely just to get you thinking, okay? Average rate of change is how much a function changes over a certain interval. So that's, yep, I like that. So we're looking at how much the average rate of change is how much a function changes over a certain interval. So if you've got a function, let's just talk about a parabola, from here to here, from this point to this point, how much does it change over a certain function? You just do a straight line and calculate the gradient of, or calculate the rise over run of that, which is the gradient, which is really what you're doing. Instantaneous change is how much a function changes at a specific point. Again, I mean, you could sort of talk about this as a single point, but this is probably a bit better because we're talking about how much a function changes at a specific point. So if we talk about at a specific point on a function, it is right there. Now, a function comes from a rule, and even if that rule is a specific point, it still has an equation. So if you've got an equation, you've got a function, then you can actually talk about, well, even if we said, you know, of this function, you know, it was only 2, like it was an element of 2, right? We're just talking about the element of 2. Then technically you could still calculate the gradient at that point because you know what the equation is, and you know what the gradient is. And how do you know what that is because you could really, what we did last time is zoom right in, you know, you could substitute in 2.001 and 1.999, and you could look at the rise over run between those two. But again, it wouldn't give you the instantaneous rate of change. It would give you a pretty good idea what it is, which really, when you round it down, it does. So average rate of change is the slope of the straight line between a range, which is pretty good. I like that one. I do like this one. This definition to me, I just personally clicked with for me, and that's why I said take down any that you like for that, because you can sort of talk about that. While instantaneous is the gradient of the tangent on a slope. Now, I do prefer this definition probably over, I do like this instantaneous one of that, but I like the word tangent because you can actually then calculate it. While the instantaneous is the gradient of the tangent on a single point. So what we're talking about there is if you've got this graph, right, and we've got a single point here. Now, a tangent line, as you guys know, if we zoomed that right in, right, so that's just say that's your slope there, right, that's slightly sloping. A tangent line would just, I haven't done it, damn it, it would just touch, oh, it's so hard, I feel like Ryan, would just touch the graph. There we go. Okay, it wouldn't intercept it. So this tangent line would, its gradient would equal the gradient, let's call that point A, the gradient at point A. The gradient at point A. So the tangent gradient would equal the gradient at point A. Of the function. So that's what we're really trying to say. Because if you draw a tangent line to that and it doesn't intercept it, that's what a tangent line is. Because if you drew it slightly off angle here, it would intercept, right? Or if you drew it a bit more this way, it would intercept a bit earlier, like it'd have to go through 2 points and then through there. So the tangent line, which I really think is good definition, but if you don't quite understand what a tangent is, well, that's probably where you're not quite getting it, just touches it, okay? And remember, we call it a tangent line. Funny thing about tangent, what is tan? Well, tan is opposite over adjacent, right? Opposite over adjacent. It's rise over run. And that's why we call it a tangent line, because it actually tells you what the gradient is. So I do like that. And instantaneous is the gradient of the tangent line at a single point. That's cool. So you could just draw a tangent line on, right, and then calculate the gradient of that. Now that's going to be pretty hard because if you're like me, I can't really draw graphs really quite, accurate. And putting a line on there and calculate what the angle is would be pretty hard. So we're going to look at how we find this instantaneous rate of change. So we all know what average rate of change. It's just literally finding, if you've got a point here and a point here, and you want to find your average rate of change, what you're really calculating is your rise over your run. Right? Because if you draw a straight line, if you want to know what your average rate of change is, well, you do your difference in your y over your difference in the x. I mean, that's all we're doing, which is another word for, if you look at difference in y over difference in x, is really another thing. What you're calculating is your gradient. So you're really just calculating your gradient of 2 points. So you could say the average rate of change is the gradient between 2 points. Or you could say is a straight line between 2 points and you're just calculating the gradient. So that's what we're sort of looking at. It does calculate the gradient, and then you've just got to look at what units your rise is and what units your run is, and that would be what it is. So for example, if it was, kilometers per hour, if this was our axes, km here, hour down here, this would be the average rate of change, calculate that, which is m, and then it would be kilometers per hour. Right? So it's literally just that. Any questions on that? If you guys can just give me 0 to 5 about how well you've understood this, and if that's pretty clear to you, that would be a 5. 3, I got some of the things, but some of the things I got lost. 0, I have no idea what you're on about, Mr. Rainbow. That'd be great, just in the side. Thank you. I don't want to move on from there too fast. Just if you can all please put it in, that'd be great. Okay. I really don't care if it's a 1 or a 0. All right, I'm going to keep on moving on. I will keep on looking at those numbers coming in on the side. So we're going to look at, okay, we've talked about average rate of change. Now we're going to look at instantaneous rate of change. Now let's just talk about average rate of change. We'll quickly have a quick review of that. So this graph is y equals 2x squared. Okay, so it's just a parabola, goes through here, 2x squared, 1 would be 2, 2, put in 2, 2 squared is 4 times 2 would be 8. All right, so you can see there, that's sort of the graph that we're looking at. Now, if I want to find the average rate of change between x equals 1 and x equals 2, obviously what I'm going to do is I'm going to figure out the values here. So we know that this point here is going to be 1, 2. And we know that this point here is 2, 8. So my average rate of change between these is going to be 8 minus 2 on 2 minus 1, which equals 6. So my average rate of change is 6 units. Really, hopefully what I was trying to get you guys to realize with this is all you're calculating is your gradient, right? So what we're actually looking at throughout this study is the gradient. We're just analyzing the gradients. That's all we're doing. And what we call that is I suppose part of that comes through differentiation. So we're going to try and find out how can we calculate the gradient at any point, but I want to know it instantaneously. Or how can I find it out over an average 2 points? And there's a couple of rules that come with that. We're going to look at first principles today, and then there's also another one which is just doing differentiation by rule. But we're going to look at first principles to try and make a bit of sense of this. So if I wanted to calculate the difference between these 2 points, okay, what I can do is I know I've got this point 1 and 2. Well, what happens if I wanted to know the point between 3? So let's just say if we had point 3 I don't have on here, but if we obviously put in 3 here, 3 squared would be 9, that would be 318, right? So I know that that would be, now I've got, what have we got? 18 minus 2 on 3 minus 1, that would equal 16 on 2, which would be 8, right? So that would be 8. Now, what happens if I had this fixed point, 1, 2, but I wanted to know the average rate of change between any point? So, for example, I want to have a variable. Well, all of a sudden, I have a point 1, 2, but I could have any point on here, right? And I'm going to call this, this other point, what would it be? What would this other point be? Well, these points need to take on another value. Well, this would obviously then be an x value, and this would be y, right? Now, if I tried to figure out the actual gradient of this, it would be pretty tricky because I'd have to be like, okay, well, my rise is y minus 2 on x minus 1. Well, that doesn't really help me because, you know, if I want to go, oh, what happens if x is 3 or x is 2? I mean, I can't go 2. I've got to go back to the equation and substitute 2 into here, right? So what I'm going to do, instead of writing this in terms of y, I'm going to put this in terms of the function, okay, which is 2x squared, because then that would really give me, you know, where I'm at, right? I mean, then I could figure out what the value is. So I could say, well, really, this is 2x squared minus 2 on x minus 1. Now I could find out the average rate of change between any point, right? So, you know, if I knew that I want to know between this point and 2, 8, I can just substitute in what x is 2 into here. So let's just look at that, how that works. So hopefully we should get the same answer as this. So I've got 2 times 2 squared minus 2 on 2 minus 1. 2 squared is 4. 4 times 2 is 8. 8 minus 2 is 6. Hey, that's 6 on 1. That still equals 6. If I put 3 in here, that would still be then, you know, 3 squared. If I put 3 in here, 3 squared is 9 times 2 is 18. 18 minus 2, and that would be 3 minus 1. So you can see how I've made a rule now from this fixed point to how I can find out the average rate of change of anything. Just 0 to 5 on how you guys feel about that, what I've done here. So I've just literally, you know, created a bit of a rule to find from this fixed point what the average rate of change is to anywhere. Cool. Okay, thank you. So we're going to keep on looking at this sort of concept. Now, that's one way to look at it, putting in here. So if I wanted to find out the instantaneous rate of change at this point here, right, I would then need to substitute in 1, 2. Okay, so let's look at that. So we're going to try and find out that this is good for finding an average rate of change. Now, this is where the problem came in, and we're going to look at this problem. So we've got this rule, which tells me the average rate of change from this point here. Now, if I want to find out the instantaneous rate of change from that point, I could just substitute in this, right? So let's substitute in that point. So we're going to substitute in x for 1. So it's 2 times 1 squared minus 2 on 1 minus 1. 1 squared is 1. 2 times 1 is 2. 2 minus 2 is 0. That's all right. 1 minus 1 is 0. Uh-oh. When we divide by 0, that's undefined. Huh. So you're telling me the gradient here is, either undefined or it's vertical? Does it look like it's vertical? No, if I drew a tangent line to that, it wouldn't be. Also, I know if I really zoomed in and calculated that, so let's just actually calculate, like we could calculate what it was by doing a small difference in x over a small difference in y. Let's actually see what that is. So let's try and calculate what the instantaneous rate of change is for this. So I'm just going to slide across for this rule. So this is y equals 2x. So we have that conundrum, 2x squared. So we're going to substitute in just y equals 2 times 1.999 squared. And we're going to substitute also in 2 times 2.001 squared. So we're just looking at, like, you know, these 2 points. We're zooming right in on the thing. Here's point 2, right? And we're going to look at the x coordinate of 1.999, and we're going to look at the x coordinate of 2.001, because if you zoom in enough, it will be a straight line. And we're going to calculate the rise over run of those 2 points to figure out what that is. So I'm going to pull up my CAS. So this is just how we did it in previous chapters, just looking at, you know, instantaneous change by looking at a small difference in x over a small difference in y, right? I mean, that's what we've done. We've done a small difference in x and a small difference in y. So what is the instant rate instantaneous rate of change. Even though it's not really instantaneous, it's still average, but it's probably the closest we can get at the moment. So we'll look at this, and we're going to look at this, and we're going to look at how basically people overcame this. So for this, we'll have a y coordinate. Got to close my brackets. We will have a y coordinate of this one. We've got a y coordinate of 7.99202. So that's what y equals. So that is this coordinate here. Right, whatever that one. And then the other one is to the power of, I'm just going to actually cheat a bit. Not cheat, I'm going to be smart and efficient about this. Just copy that down and put in 2.001. And that one's going to be 8.80000. Now we can do rise over run. So it's going to be, let's pull up a keyboard. So we will pull up this one. And we're going to go this one minus this one. So that's my rise. That's my difference in my rise. Why? Because, you know, this coordinate here is going to be the 8 point. It's going to be this one. Y equals 8 point. What was it? 0.08002. So that's the 8 one. So we're doing the difference in my y over my run, and my difference in my run was, well, we start off with the big one, so we've got to start this coordinate first, so we've got to use this one, 2.001 minus 1.999. The gradient at that point should be 8. So we've got a gradient of 8. Now, when I tried to do this method, it gave me an undefined, because I've got this denominator of 0. So, okay, maybe what we could do is we could play around with this bit, and maybe instead of using 1, what we could do is we could use, like, you know, because we want to find out the gradient at that point. Oh, we found out the gradient at 2. Whoops, not at 1. My bad. I just realized what we did. We'll find out the gradient at x equals 2. Sorry, which is where I wanted to move on to later. So we actually found out the gradient at this point, not at 1, which is fine. We can still work on that. So we found out the gradient at this point because we just substituted in 2 and 1.999, which is, yeah, okay. Even if we want to calculate the gradient of that instantaneously, we'll go back to the gradient of this one. Let's calculate the gradient of that one. Actually, instead, we'll quickly put that into the calculator. We'll do that as well. I just realized I made a mistake, but that's okay. Good review for us. I'm sure some people probably try and tell me on the side. So we go y equals, we'll do another one. So we've got 2x squared as our rule. So we'll put in 2 times, 1.001 squared, and we'll also put in 2 times 0.999 squared. So we're going to look at these 2 points. We're basically looking at 2 points where 1 is in between, and we're also looking, this is the x coordinate 1, and the x coordinate here will be 0.999, and the x coordinate here will be 1.001. So we're going to look at the difference of the rise over the run of these two, because then we can get the gradient of that. So let's just quickly put that in. So we're going to have 2 to the power of 1.001 squared. We got, oops, that should be 2. And then we've also got 2 to 0.999 squared. Okay, we're going to look at the rise over run. So I'm going to pull out a so difference in y. Over difference in x. Gradient of 4. So the gradient at this point is 4, right? So we know that our m value at when x equals 1, we have a gradient of 4, okay, there. That's what we're trying to show. So we have a gradient of 4 at this point right here. But we realize that when we tried to do it using this, it didn't work. So what we could do is, and what people started to try and discover, and this took years of discovery, by the way. So people were trying to come across this, and we're going to learn this all in one lesson. So you're learning like someone's whole life investigation in the matter of, a couple of hours an hour. So I just like to, invest in time into this, because I think just someone put their whole life to this, and it's just a beautiful piece of maths. So what we could say though is, because if we substitute in 1, it didn't work because we're using it from this point. Well, what about if we just like use the point 1 and use like 1.001, because that's a small difference over us. We could do that. And let's see how that works. I mean, that should give us a gradient of 4 as well. So we've got 2. So we'll bring up another fraction. So let's look at that. 2, 1.001 squared minus 2 on 1.001 minus 1. That gives us 4.002. Now, it's not bad. It gives you a pretty close answer to it, but we know that it's probably not 4.002 because it would really be 4. Because obviously what we've done here is we've used, this point 1 and that point there. So it's slightly gone up. But if we use either side of it, we can probably get a better idea, of the average. So that's why we've got the 0.002 in there, where before we just had 4. So it's okay. It gets you close to it. So you could say, oh, it's pretty much approximately 4. Well, it is 4. But the mathematicians didn't like this because they know that it should be 4, because really if you're taking what we've done there is we've calculated from this point to this point. So that's going to be a slightly different angle compared to calculating this point and this point. And that's why we got 4. So the mathematicians didn't really like this. They didn't like this 0.002 on the back because they sort of knew that it should be 4. But how can we mathematically prove it? Because when we use the same point, we get to 0. And this still isn't instantaneous, right? I mean, there's still an average. You've got different points in there. It's minuscule, but there's different points. And it drove them insane. So we're going to look at how we can actually make that an instantaneous point. Let's look at this. So we're going to look at these same points. So again, this is exactly the same graph, okay? So we've got the point here, 1, 2. So what we actually decided to do is define this a little bit differently. So if we wanted to look at the 2 difference between these points, the same thing again, they said, well, how can we get rid of that? Well, let's try something a bit different. Instead of putting in these points, let's actually put in a variable, h, where h is the distance left to right, the horizontal distance between the 2 points, right? So instead of using a point here, we're going to use a point h. So this point h could take on any point, this distance could take on any point, positive or negatively. So for example, if h from here was -1, it would be down here because it would have a horizontal distance of -1 because this coordinate's 1. If h was 1, the point would be here. If h was 2, it would be 318 or whatever it was. If h was 1.5, then the value of the x coordinate would be 2.5, and whatever the y coordinate is that corresponds to that. If h was -2, it would be over here because it's -2. If h is -3, well, it would be -1, -2, -3. So that would be the point here on the function. So do you guys understand what h represents? It represents the horizontal distance from this point. That's what it is. So we're just talking about the horizontal distance of that, and that's what we did. So how can I find out the distance? How can I find out, for example, what this point is here? So h could be a variable. So now all of a sudden, instead of having a fixed point like we did before, where this is, 2 or whatever, or x and y, let's give this a variable instead. Because when we use the equation before, if we tried to give it, use the variable x in the equation at the very start, which is what we tried to do. If you try and get to the same point, if you try and give that point, it could be anywhere on the equation, it could be y, minus x. The problem is that we had a 0 in here as soon as you get to that instantaneous point because you're minusing the same number from each other. So I know, let's just give it a h. Okay, we're going to try something a bit different. So what is this point? Knowing that this point could be anywhere on the graph. It could be anywhere, right? Well, what is it? Well, this point here, really, if this is H here, so H could be there, or, H could be here, you know what I mean? So the value of H is really, what's the coordinate here? What's the X coordinate? Well, the X coordinate, well, you've started at 1. So it's going to be 1 plus I've moved across H, right? Like it doesn't matter. If it was here, it would still be 1 plus H. If it was here, this point here, the X coordinate would still be 1 plus H. But I know the value of H here is -2 in this case. So what I've done here is really I have put in a variable for how far apart the horizontal distance is between 2 points. So if H equals 0, I would be back at this point. If H equals 1, I would be 1 across. So I'd actually be at point 2, which is here. If H equals about 1.25, I would actually be at, from 1 plus 1.25 would be about here, would be this point here. If I went H equals -2, well, 1 plus -2 is -1. That is here. So I've now got a variable to move this. Obviously, you might be able to see if we actually let H equals 0, that might give us our instantaneous point of change. And that's where we're going. 0 to 5, if you understand what this H represents, just that it's a horizontal movement and it can be anywhere on the graph. That's probably the hardest concept to get. Excellent. Stick with me because this journey, is like a good decade of learning, and I think it's, incredible. All right. So we've got this horizontal distance. I mean, technically at the moment, it's not a coordinate because if you said, well, H is 1, 1 plus 1 would be 2, would be here. If it was 1.25, it would be here. If it was -2, it would be here. If it was like +3, it would be here. But we need it to actually have a coordinate on the function, right? We need this to have a coordinate on the function because we really know that, well, if we want H to be 1, it should be up here. So how do we get it to be up here? Well, don't forget the equation came from y equals 2x squared. I mean, that's where it comes from. So how can I get the y coordinate? So if this is 1 plus h, right, if it can be anywhere on the map, how do I get this h to correspondingly go up and down for its y coordinate? Because at the moment, if I just add on h, it's just going to move it across left and right. But I've got to give this a coordinate of any point because otherwise it's just going to make a, it's just going to give it just the 1 point, right? It's just going to be a vertical line going up or down because we've only given an x coordinate. It's like saying, 2 as my x coordinate. You're going to be like, 2 where? Okay, so obviously it's just the whole thing. So you're just saying x equals 2 because at the moment we're just saying x equals 1 plus h. Well, 1 plus h could be anywhere, right? So we've got to figure out the y coordinate. Well, the y coordinate corresponding to it, well, I've got to actually substitute in. If this is my x coordinate, I would need to substitute into the equation to find out what y equals. So y equals 2 lots of 1 plus h all squared. That's my corresponding y coordinate. Because if I was 2 across from horizontal, I could just substitute 2 in here, right? And then that gives me, 1 plus 2 is 3 because we started at 3, which is that is 3, then you're just putting in 3 squared. If I put in, -2, because h is -2 from here, we're talking about it, 1, 2, you'd be at -1. Well, 1 plus -2 would be -1. Hey, that's x equals -1. So do you see how this gives me the y coordinate of any point? Because h is the horizontal distance from here. If I put in 1 here, it's going to be, if h is 1, really that has an x value of 2, right? And notice that it does that. So all we've done is we've just put in plus h, which is a horizontal variable, and we've substituted that coordinate in because this point could be anywhere on the map, which is 1 plus your horizontal distance. So the x coordinate, the y coordinate then would be 2, 1 plus h all squared. So that's my coordinate for any of these, 1 plus h 2, 1 plus h all squared. And this coordinate here is 1 plus h, and the y coordinate be 2, 1 plus h all squared. So all these coordinates are that, because here, this would have to be -2. My horizontal distance would be -2. Putting -2 here, it would be -1. -2, 1 plus -2 will be -1. -1 squared is 1. 1 times 2 is 2. Look, it gives me the coordinates 1, 2. Here, we know that the coordinate's going to be 2, 8, but the horizontal distance is 1. Put in 1 here, that would be 2. The horizontal distance is 1 here. That makes it 2. Notice how it makes the x become 2. 2 squared is 4. 4 times 2 is 8. So hopefully you can see that, that works as the x and y coordinate. So all we've done really in quick short, I'm going to summarize it really quickly now because hopefully you've understood it, is if we have a point and we want to know the instantaneous point at that, well, let's introduce a variable of a horizontal distance from the x. We're going to introduce that as any point on the map where I'm at plus h. The y coordinate is, well, I know this is the x. I'm just going to substitute the x coordinate into my equation. That's my y coordinate, because that's what x equals. I've substituted that in. That's it. Now what we're going to do is we've got 2 points. I've got this point and I've got any point on the graph, right? What I'm going to try and do is get h to approach 0. Let's try and do this. Let's try and do the instantaneous rate of change. Now the instant rate of change is rise over run, right? Rise over run. But we've got a variable here. So let's do the rise over run with this one. So my rise is going to be 2, 1 plus h all squared minus, because this is my y coordinate, 2 over 1 plus h minus 1. Does this make sense that this is my gradient? So note before we tried to figure out what the average rate of change here. If I put in 1 here, that will give me my average rate of change between here and this point, because that's 1 to the right. So 2 times 2 squared, that would be 4, 8. 8 minus 2 is 6. 6, and this is 1. 1 plus 1 minus 1 will be 1. That gives us a gradient of 6. Can you guys see that that would be a gradient of 6 if h equals 1? If I put in -2, we know that the gradient should be 0, because the average rate of change between these is 0. Putting -2 in here. 1 plus -2, that's -1. -1 squared is 1. 2. 2 minus 2 is 0. And down here, you're going to have -2. 1 minus 2 is minus 1. Minus 2 is minus 1. 0 divided by minus 1 is still 0. So it gives me the gradient at any point, the average rate of change. If I now try and put in, I know, let's do the instantaneous rate of change. Let's make it equal this point. Let's make h equal 0, because if we bring this horizontal distance to nothing, what happens? Let's check out that. This is going to be excellent. Oh, we're going to find out the instantaneous rate of change, right? This is so cool. Oh, you guys are going to love this, right? 1 plus 0 minus 1. Oh, we're nearly there. This should be 0, right? We're going to substitute in 0. So we're talking about the horizontal distance is nothing. It is at that point, right? So we've got 1 squared is 1 times 2 is 2. 2 minus 2 is 0. Uh-oh. And we got 1 plus 0 minus 1 is 0. Oh, are you serious? This still equals undefined. All that for nothing. Okay, that's okay. Don't worry, because we really need to get rid of this denominator, right? I mean, what made this go to 0? This h made us go to 0. Can we get rid of that? Well, let's see if we can get rid of that somehow. Can we get rid of that? Can we get rid of that or not? And that's what we need to look at if we can. So what I'm going to do is I'm going to expand this out instead of here. I'm going to expand this first one out, and this is what we need to do. So this is going to be 2. 1 times 1 plus h squared will be, 1 plus, we're going to have 2h plus h squared, right? That's what this expands out to be. minus 2, 1, plus h minus 1. I'm going to work down the page here. So now I've got 2 plus 4h plus 2h squared minus 2 on, well, 1 minus 1 is just 0, right? That's all on h. 2 minus 2 just leaves me with nothing. This is going to now leave me with 4h plus 2h squared on h. I'm getting excited. Why am I getting excited? Hang on a moment now. I can get rid of this denominator. OMG. All right, here we go. This is where first principles stumbled across something that was just like, this is awesome. I can get rid of this. This is actually going to be 4 plus 2h. And this is what our gradient equals, don't forget. So hang on a moment. You're telling my gradient now, if I let h equals 0, my gradient is going to be 4? Ah, that's what we just found out earlier. We did it. So the trick here is that we actually made this horizontal distance, right? We introduced it. We have our y coordinate, we have our x coordinate of it, and then we have another point. And then all we did is we just expanded this. And when we expanded it, because if you don't expand it and you just put in 0 here, you get a denominator of still 0. But when you expand it, the interesting thing is these two constant numbers, they actually just go away. And down the bottom, the constant numbers go away because you've got the 1 and you're minusing the 1, right? Here you had the 2 and you're minusing the 2. So then you're left with just h's and you got the h on the bottom and you can get rid of that. So what this means is this is a rule that tells me the gradient from this point here. So we've got 4 plus 2h. So it tells me that I can find out the gradient or the average rate of change or the instantaneous rate of change from this point to any other point is going to be this. So if you recall, what was the gradient that we found out between these 2 points was 6. So what's the horizontal distance between these two? The horizontal distance between here and here was 1. Well, this is our gradient. If we put in h equals 1, notice it gives me a gradient of 6, right? It gives me a gradient of 6. This is what m equals, right? Well, we also knew that when we had a horizontal distance of -2, the distance, the gradient was 0. Okay, 4 plus 2 times -2, that is also going to give me the gradient of 0. So if I have a horizontal distance of -2 for this question, that means the gradient between those 2 points here and 2 less is 0. Okay, if the gradient between these 2 points, 1, which is further to the right, would be 4 plus 2 lots of 1. The gradient for that equals 6. So that is first principles. That is how we can calculate the gradient from one point to any other point on the graph. And we can get the average rate of change. Or if we let h equals 0, we can get the instantaneous rate of change. We've created a rule for that. 0 to 5 about how well you've kind of comprehended that. I really need your feedback on that one. I'm getting excited too, Ryan. I think this is great. I just think it was just so cool how they, like, you know, you run into this thing, it's like, oh, it's still undefined. Oh, hang on. If we expand it, hang on, we can eliminate that denominator, and that denominator of 0 is the trick. If you can get rid of that trick of the denominator being 0, you come up with a rule. Oh, it's just beautiful, right? You can see where the gradient is. It's so cool. You know, we've made it like a function from that point. We can find out the average gradient from that point, or we can find out the instantaneous gradient if we let h equals 0, and you get that beautiful number. Like, we know it's 4. We can prove it. Yeah. Yeah, I know, James. You can be like that. All right. So what I'm going to do there is that really is how we do it. Okay. The next trick is probably the same kind of thing. So there's where we find the gradient from a point. Okay, that's what we've done here. We've found the gradient from a point, which is fine. So we've done that. What happens though if we change it up a bit? And I'm just going to change this up a bit. And I'm going to now just show you guys how we can use first principles. And it's going to give us a rule for anywhere on the graph. It's exactly the same thing. I'm going to go through this probably a little bit quicker because I know you will get a bit lost in here and we'll review it again. So before we had this point, but that's cool. That just gave me a point. We got a function, right, of 4 plus 2h, right? And that told us the gradient from there. But if I want to know what the gradient is here, I would then have to calculate it differently. And if I wanted to know what the gradient, instantaneous gradient was there, I'd have to calculate it differently. So what I'm going to do instead is I'm going to actually just call this point any point on the graph. Right? Now, remember our function was 2x squared. So really, this point here, I'm not going to write as that. I'm going to write it as x 2x squared. Because really, that's going to give me my y-coordinate. Like if it's 1, you put the number in here. That would be 1 squared, 2, that gives you 2. If it was 2, 2 squared is 4 times 4, 2 is 8, right? So it gives you that point. So this is my x, y coordinate. Now this can be a point anywhere on the graph. Are you with me? Do you guys understand that this can be any point on the graph? I've literally written the x, y coordinate in terms of x as any point on the graph. If you can give me 0 to 5 about that, that'd be really good. Do you understand that that x and that y, this represents any point on the graph? It just depends what number you want to put in for x, but it will give you the point, like it slides around with it. Awesome. You guys are absolutely doing unbelievable. I was really worried about teaching this to you remotely, but thank you so much for your feedback. If that's true, that's absolutely great. Okay, so if that's any point on the graph, well, let's do the same thing again. Let's just introduce that h value, right? So now what we're going to do instead is I'm going to actually come up with a function for any point, the gradient for any point on the graph. Because before I was based at 1, 2, but this time I can do the same thing, but base it from here. So all we're going to do is we're just going to have a horizontal distance. So this point here would be, well, x plus h, right? You've gone horizontally across. And because I've got to keep it mapped to here, I need to substitute that into the equation. So that would be y equals 2 lots of x plus h all squared, right? That's my coordinate here. So this is going to be 2x plus h all squared. Can you guys understand how I got this point here? 0 to 5 would be good for that one. So all I've done is I've got any point on the graph, and then in relation to any point on the graph, well, this is just it. Because just say if x was 1 here, well, let's say what it is. Let's just say x is 1.5. Let's call it 1.5. It's 1.75. And just say I went like 0.5 across, that would be, well, 0.75 plus 0.5, that would be 1.25, right? And then this would also be 1.25. So can you see how it works in relation to this? Hopefully you can. So really we're just talking about any point of x, whatever you put in, and that would be the horizontal distance to it. So what we're going to do now is I'm going to do my rise over my run. I'm going to find a function for these two to find the gradient between the 2 points. So we're going to do rise, which is 2x plus h all squared minus 2x squared on x plus h minus x. So remember, this is just literally rise on run, which is really just y2, which is this one, y2, minus y1, which is this one, on x2 minus x1. x2 minus x1. What does this simplify to? Well, we expand this. That's going to expand to and our denominator, hey, we're just left with h. That's good news. Now I can expand the top 2x squared plus 4xh plus 2h squared minus 2x squared on h and just watch me on this one if you're trying to write it down. I will leave this one up because I'm going to finish on this, but just try and follow me through on this, and then you guys can take down your notes. This one's going to be then, well, 2x squared minus 2x squared would just leave me with nothing. So I'm going to be left with, and I'm just going to draw it over here. I'm going to be left with 4xh plus 2h squared on h. Guess what I can do, guys? I can eliminate this h. I'm getting excited. So that is 4x plus 2h. How cool is that? So that will give me the gradient of any point, right? Any point on the graph between 2 points. So say if x is 1, like what we did before, and the horizontal distance is 1, the gradient should be 6, because we knew that from point 1, 2 to point, what was it, 2, 8, I think it was. The gradient should be 6, because the rise over run is 6. So let's check that out. If we put in x is 1, so we'll choose this point here, x is 1, and the horizontal distance is 2. So if you put in 1 there, x is 1, so it's going to be 4 times 1, and the horizontal distance between these 2 points is 1, plus 2 times 1, the gradient equals 6, which is right, okay? The other thing I'm going to show you, though, what's really cool is let's try and use it as an instantaneous point. Well, I know that if it's instantaneous, h has to be 0, right? So what we're going to do when we want h to be 0, I'm going to get h to become 0. So we're going to go with h. We want to approach that to 0, right? And if we approach h to 0, we actually have that as a limit, and I'll introduce that probably a bit later. We can find that it equals just 4x if we let h equal 0. And that's where, you know, we'll get to that one there. So, because if I let h equal 0, it just is 4x. So what does this mean? So this gives me the instantaneous gradient at any point for x. So hang on, if I put 1 in there, the gradient is 4. Remember when we found out the gradient back here was 4, if you put 1 in there? So if I put 0 in there, the gradient is 0. Well, the gradient here looks like it's 0. If I put -1 in there for x, it gives me -4. Well, that would be right because it should be the opposite. If I put 2 in there, the gradient is 8, it's saying. Is it? Yep, it must be. So we can see what the instantaneous gradient is in there. And if you actually look at those values, so where is my CAS? If we put in, for example, you know, what other values do we try and find out? Yeah, we found out 2. Remember how we found out the gradient? Remember how I made that mistake at the start, which I didn't on purpose. But right at the start, I calculated the gradient at x equals 2. The gradient when x equals 2 is 8. No, it's not. Sorry, the gradient when x equals 2 was, what was it? Did we write it down? Gradient when x equals 2 was, here it is, 8. It is 8. I did the calculations there. So the gradient when x equals 2 is 8. Now, if you go back to this equation, if you put 2 in here, it tells me that the gradient is 8. So what we've actually done is we've created a rule to find out the instantaneous gradient at any point on this graph, which is 4x. So I can literally substitute in 1. It will tell me my instantaneous point of gradient, there's 4. If I substitute in 2, my instantaneous gradient there is 8. If I substitute in 3, the instantaneous gradient x equals 3 would be 12. Because we've eliminated, we said, hey, let's make h 0. Now, I could have left it like this and I could find the average gradient. But as I said, we want to be more, I wanted to look at just the instantaneous point of view. I will leave that up there. It is a very tricky concept, as I said, this one, the first principles. I will encourage you guys to please try a couple of questions for me if you can. One thing I did want to show you, though, is how you actually do your annotation of this when you're doing it mathematically. And I'll refer you to the book just purely because we're running out of a bit of time. So when you are doing differentiation by first principles, in terms of the annotation that you want to use, not that one. not that one, this one here. Okay, so we want to, they don't even have one here. So yeah, we want to basically, if you're finding the gradient of this point and another point from it, a tangent to the curve. So what we're trying to say here, this point is 2, 8, and then we have a horizontal distance from it. So it's 2 plus h, and because this is the equation, you've got to substitute 2 plus h cubed into it, would be your y coordinate. So you're going to do your rise over your run. So it's y2, which is this coordinate, minus 8, over your x coordinate, 2 plus h, minus your x coordinate. Then you expand it and simplify it. You'll find that you'll be left to eliminate h's, which will leave you with this. Now the gradient of the line at 2, 8. So if we want to find out the gradient, find the gradient of the curve at the point 2, 8, that's the instantaneous point, right? Because it's saying find it at that point, not a function for it from that point or for the average rate of change. We're saying we want to find out the gradient at that point. If that's the case, I've then got to do a limit as h approaches 0 because we want that horizontal to be 0. If you substitute h equals 0 into this, you're left with 12. So the gradient at that point is 12. So that's using a point with first principles. Alternatively, sometimes we're going to ask you guys to actually find a rule. We want you to find the rule where the instantaneous gradient at any point on the graph. If that's the case, you're going to use the x coordinate and the x plus h, which is my last one. And then you'll find what we did there. But when you're doing your annotation for the rule, you're going to do function. If it's a function, you're going to do f dash x, and you're going to do equals limit h0 all the way. So what I mean by that is over here, what I should have done when I was doing this, where did my pen go? But I didn't want to really do the annotation, and don't worry too much about the annotation. We'll fix that up as we go through, because this is why I should actually have done it as dy on dx equals, that should be an equal sign. I'm probably not going to have it here. Limit as h approaches 0. That really looks bad. I'm going to do it over here a bit neater. Dy on dx. So this is what should be on every line, because I'm trying to find a function, a rule for the instantaneous gradient at every point. Anyway, I shouldn't have done dy dx, actually. I should have done function. I should have changed this to fx. My bad. Because dy dx would be doing a bit different technically. This should be all fx. This should be not dy dx. This should have been f dash x, which means this is the derivative. So this is what we're doing. We're doing the derivative by first principles. Sorry, I did that very bad. Let me see if I can get that all back. I probably can't. Don't worry too much about the annotation. I really want you guys just to get an understanding of the mathematics of it, of understanding if you want to get any point on the graph, you've got x and you've got y in terms of x, which is literally, which is 2x squared. Oh, now my pen's gone. Which is just this point, right? 2x squared. Then what we do is you're going to have x plus a horizontal distance. Then you substitute this x value into the equation, 2x squared. That's the x position. Then we're just going to find out the gradient between these 2 points. y2 minus y1. y2 minus y1 on x2 minus x1. Expand this, simplify that. When you've expanded it, you'll find if you've done it correctly, you'll only be left with h terms with h. You'll just have h down the bottom because they will eliminate each other. You'll find that this 2x squared or whatever you've got up here will be eliminated, and you'll just be left with h's if you've done it correctly. Eliminate your h, you're left with a rule. Then we let the limit of h equals 0. Let h equals 0. You come up with a rule of 4x. That now tells me the instantaneous gradient at any point on the graph. I can just substitute in what x equals. That's how you do it for a rule. If you've got 2 points, we do it the other way. And it's all gone on me now. Good old ones. So I'm going to leave it there for you guys. hopefully that introduces first principles too. I really get excited about it. I think it's just a magical piece of maths. And good luck with first principles. It's literally just rise over run, and it's a horizontal value.